Perfect. Let me first say hello to everyone, and I hope you guys have a good and fruitful day in Berlin. Let's try to make this work with a remote connection, but I think we're gonna manage. So I'm gonna talk a little bit about simulation in high energy physics in particular, because that's my field of expertise. So should only talk about this, where I actually have something to say for you what might be interesting. And the main topics I will show are basically how we use simulation at our physics laboratory in Geneva, which you might know. I'll have 2-3 slides to give you a brief overview what we do, but then I'm going to jump into the technique and hopefully show you something you can make your own picture from. So if you go to slide 2, slide 1 you can skip. This is just the title slide. So let's go to slide 2. This is an aerial view of our particle physics lab at in Geneva, with a multi-stage accelerator complex. Everything is underground, so you would not see these nice lines drawn. Of course, if you flew over and landed at Geneva Airport, you can see on the right side a little bit the landing fields. And you see our two colored in red laboratory areas where we work, and then you see outlined here in this with this white rings a schematic view of the accelerators. The main ring, as you can see here, is 27 kilometers long and is 100 meters underground. So there's an injection of particles. They will be accelerated to or close to the speed of light, and then we have 4 places on the ring where we let those collide. So if you swip over to slide 3, you can see this a little bit more, the ring again as seen before, and now with the 4 points where the 4 experiments are situated. So if you start going one further, you see basically the ring underground and the 4 experiments with their acronymous names. I will not go through. You can read it up later on another slide. If you go one further, you see like schematic views of these detectors. I will come a little bit to this later. And 2 more further, 3 more further, you can see just an overall table of the experiments and their size. And this is a bit interesting and will be interesting for the rest of the talk. And I hope I'll make that clear to you afterwards. So the experiment I'm working on actually is the first one, called the Atlas experiment, which is a quite randomly chosen acronym. As you can see, you can, I think, always pick random letters out of a compound of words and then make up a name that fits you. But to give you some sort of an overview, the experiment is a particle detector. We'll come to that. That has a length of about 40 meters and a height of about 22 meters and weighs 7,000 tons. This is actually quite light compared to our, let's say, brother or sister experiment called CMS, which is a bit smaller. You can see the dimensions afterwards, but has almost double the weight. So it's like 12,500 tons, which is to give you some sort of a feeling. It's more than the Eiffel Tower in terms of steel. So just to give you some sort of feeling. Let's go to slide 4 though, and then it starts a little movie, hopefully. Yeah, okay, no worries. You probably have seen the movie, which does the injection of the beam into the rings, and then they will counterclockwise and clockwise the 2 rings. Basically, the particles are led, and they get into a collision inside the detector, and that's like what our primary experimental setup. Let's put it that way. So this was slide 4, and now I jumped over to slide 5, and that is a picture of the detector. So you can see during construction still, that is not yet finished, but you can see basically the extremely complex setup, experimental setup we have to deal with. And we have such a big machine to measure the smallest particles that are produced in our universe. And that rises basically the need to the rest of my talk. So this was the motivational overview in the first 5 slides, and I hope I gave you enough of an idea about our experimental setup. And I'll dive now a little bit into simulation. So go over to slide 6, please. And the first question is, why do we actually need to simulate? So flip through one. And the one good reason to simulate is because we're not good enough in maths. We just can't calculate it. So that is one reason why you simulate. Another reason why you simulate, if you go to the next, is because it's not an analytical problem. Analytical problems you can solve. Any analytical problem, you just need to go back to step 1. You're good enough in maths, you can solve it. Another reason, which is quite bound with the first 2, is it's just way too complicated to solve otherwise. Is you would sit ages and ages and ages and ages trying to solve it, while you can simply simulate it. Another reason is because it may be stochastic nature. Everything that happens is actually of stochastic nature. So we need a stochastic answer. Means we need to redo that thousands and thousands of times and look at probability density functions. And finally, the last reason why you simulate is it's just the easiest way to solve a problem. And that can be a good reason to come up with a simulation, is because it's just way easier to solve it. So that's my motivation of saying why we actually use simulation. If you slip over to slide 7, what are we actually simulating? So many people think, when they know a little bit what we're doing and they heard about the discovery of the Higgs boson and whatsoever, they think we simulate mainly this. We simulate the proton, and in this case it's not an entirely correct picture, but the two protons colliding, and then there's some process called gluon fusion, and there's some Higgs production, and then the Higgs decays into other particles which are labeled here as W plus and W minus, and these decay, and etc., etc. And this is what most people think, actually, that we spend our simulation in, that we simulate the physics process. It's true, we call that specific event generation, or this specific part, but that takes only up to, I think at the moment, 5% maximum of our simulation budget. So the actual process is only 5% of what we actually use our simulation for. The question, though, is where does the rest go? And the answer is slide 8, which you have seen again. It's a detector. We simulate our detector. We need to simulate, basically, how we can measure this thing, because this is 40 tons of material, electronics, whatsoever you can think of, and the particles traverse through that, and we need that to measure, but it's such a complicated system that we need to precisely simulate how we actually measure. So if you think of that, go to slide 9, please. On slide 9, you see on the left side this little dot. That is the physics process. This is really the glorious, whatever, supersymmetric particle appearing, or whatsoever, what favorite theory you're fond of. You simulate that, but then most of the time, after you inject that into your model of the detector, you simulate what the detector sees of it, and not the initial process. So this is summarized if you go to slide 10. Actually, my little cartoon, which I tried to see you. So the object itself is not the difficult thing for us. The object is the thing we want to look at the end. But what our problem is, our detector, our device to observe this object, is so complicated that we need to simulate this. So what we spend most of the time on is actually the simulation of the observer. If you want to go to slide 11, you can see this actually now a little bit modeled. And on the left side, this is this second detector called the CMS detector. And what we do actually is we describe our detector setup in 3D modeling to highest precision. I will have a slide afterwards to show you actually what precision we describe it. So almost to the single screw level, and all the cables and whatever you can think of is described in a 3D model. And then we have a very precise engine that propagates the particles through and tries to simulate how they interact with the detector. And if you look at the little picture on the left side, this is actually what you see. So you see an overwhelming amount of interactions, because these particles have high energy, they go into material, they interact with material. That's the way we measure them actually on the other side. Yeah. Then they deposit energy and they scatter and they do whatever you can think of in terms of processes. And we have big machineries running to basically follow these processes. And that's one of the pictures. So when you can think of this a little bit, you can probably see how time consuming this process can be. I'll come to this at the end of my talk. So on slide 12, this is the recipe. It's the recipe for you want, if you have this flow chart, you want to end up at the bottom right, which is the Nobel Prize medal. So if you go the right way through and you end up on the Nobel Prize medal, you have done your job correctly. Let's discuss the simulation box on top. So what you see on top, that is a simulation box. So you come up with your theory of everything, of how the world works or whatever you want to do, and you generate that. You say, okay, this is like happening basically in infinitely small space, but that is your favors the particle that has not been yet found and may describe the dark matter, whatever you think of, yeah, and you generate that. Then you need to simulate how would our detector see such a signature. So that is where the entire time goes. You just like put it in and you simulate what the detector would read out of something you put in at the first. Then there's another step which is special to us, because we need to compare this at the end with the experiment. So not only do we have to simulate the detector, we also have to simulate the entire electronics. Because at the end, all we get from the detector is read out electronics. Basically, we have detection material on that, and that's related to the box at the bottom. We have the experiment. So your second stream of reality is you built the accelerator, you built the detector, you wire it up to a data acquisition system, and you feed it back in. And that is the point where the simulation meets the reality in this box called the reconstruction. Out of both worlds, we get the same input for our final two steps. So we emulate everything, we simulate and emulate everything up to the point that we get the same signals that a detector would give us, including all electronic readouts and stuff, whatever you can think of. On that, we feed into the exact same module as what we feed in the data, and then we do the analysis. And we say, do we see a signal like this? Do we see a signature that we put into our event generation, which is entirely weird, a new theory? Do we actually see it? And we compare in a statistic manner with the experiment. And then, if you do it right, you go the right way and jump down to the middle. Now, let's go to slide 13. So how can you trust your simulation? That's one of the most important things. I mean, you simulate something and then you compare it with the experiment that is built in real life. You need to be pretty much sure you understand your simulation, because if you don't, there's not much Nobel Prize left for you when someone raises their hand and says, like, well, you could have just simulated something entirely wrong, and then you compare it to data, and then you want us to be convinced that you found something. So you need to basically calibrate and understand your simulation to most detailed level. And the best thing to check your simulation in any sorts is compare it with something you know already. just simulate things you already know. If you can simulate all the things you already know, and the things you don't know already are somehow in an, let's say, phase space in a similar manner related to the things you know, you can build up trust that what you simulate is actually a right thing. And astronomy, this is often called a standard candle. So take a candle you know, you take a candle, you know how warm the candle is, and calibrate your things with a standard candle. What you can see here, for instance, is actually dated an event display. So one of these collisions already a few years ago, one of our first collisions actually in 2009, with a very nice signature. You see a particle, and if you look at the two, I'm not going to give you a course in particle physics, don't you worry, and I'm not going to ask later on any particle physics questions. But I'm gonna make a particle physics course for dummies on one slide here. If you look at the left plot, you basically look into this core of the detector, and you see two trajectories from particles that come from a common point and bend exactly the same way apart. This is always a very good signature that some particle has decayed. Because if you look at this, it's even written, it's a particle called decay short. It lifts a little bit, so it traverses into the detector and then decays into differently charged products. In this time, both pions, for those who want to then later on enroll at one of the Berlin universities for doing a particle physics education. And they propagate, they basically build a V, like a common vertex, and they propagate apart. So what you do in a little particle physics experiment, you search through all your data for this kind of signature, and then you calculate the hypothesis, what would have been the mass of a particle if I assumed these two tracks would come from one single particle that decayed. And that's what you see at the bottom. This is basically the probability of finding these things. And what you see nicely is there's some background, it just falls off. This is just stochastic. You choose random combinations, and suddenly at one specific point, you see a high probability that they all end up at the same mass. So this gives you a very, very good idea that there must be a particle that decays into these two products, and you have a mass measurement. You say it's about 500 in our mass units, and that's a particle we know. This particle has been known for, I don't know, 40, 50 years. But what you can see here, and now it becomes back interesting for our point, is we've done we knew this particle exists, we looked for this stuff, and we did that not only for this particle, because the best calibration you can do with many different standard candles, you know already. But then look at it, we did it with the simulation, and we read out the detector, and then we overlaid it. And you can see that there's a perfect match between the black data points that just basically cover exactly the filled yellow shape, which means our simulation describes this known particle to, I don't know, per mill level accuracy, and that's what we wanted to have. And if you do that and repeat that more and more often with different standard candles, you can start building up some sort of trust to your simulation, and that is very, very important. Let's go to slide 14. This is the last of the complicated slides. It will become more easy afterwards. But since I said we have the detector described to a very, very detail, this is a study we did in 2010 as well, and that is a very interesting study. What you see on the left is our 3D model of a tiny component in this massive detector. It's actually one of the innermost components. It's a silicon-based detector. And to give you an idea about the size, this entire thing is probably 5 times 3 centimeters. It's one tiny little thing in our detector. So what we did with that is we said when particles propagate through our detector, they sometimes just interact with the material, as you have seen before. Then there's a lot of particles coming out of it, and they basically die in the material. So we tried to find all these places where they interacted, and that's what you see in the middle. So you can see that's the model, and on the middle is the particle view. That's where all these interactions happen. And then we did the exact same thing with our real detector, and that's what you see to the right. So you can see quite some similarities, but one of the things which is quite interesting, which we actually where we actually found a massive difference in our modeling, and a completely stupid mistake, is if you look at the center of this description, I'll explain that very soon. You see that it looks like a ring on the right side, where it's filled in both the model and the middle plot. And that was just a very stupid mistake, because what this thing is cooling liquid. It's a pipe with cooling liquid, and that's how you would do it. You would go ahead. Liquid is difficult to model, so you model it with a box. You see that on the left side, it's modeled as a blue box. That's our cooling liquid. And it looks also pretty much filled if you look at the middle, and that's the full simulation picture. Now, when we operated the detector, it did not look like filled, but that is very, very obvious, because once you operate the detector, the cooling liquid evaporates. So it's not a box anymore, it's gas. So even though our model was correct, we just put a static model of our detector into the simulation and screwed up, because we did not think of the fact that once we operate it, this is of course not a liquid anymore, it's gas. And these are the things we did like for years and years to check that we actually simulate our detector correctly. You can imagine how much tedious work this was. So let's go to slide 15, and I come to the second part of my little walkthrough through simulation, just to give you another aspect of it. So this is such a complicated detector to simulate. To simulate one of those collisions when the two protons interact with our most accurate simulation engine, that takes 5 minutes. Unfortunately, or fortunately actually for us, when the beam interacts, so you have the beam-beam interaction, there are up to 40 of these collisions happening at the same time. And now it gets even more. These beam-beam interactions happen about 40 million times per second, and we operate on usually 70% of the entire year. Once the accelerator is running, we're actually taking data. So just to have a comparable statistics between simulation data, we need several billions of simulated events. Now do the math yourself. Take 7 billion events times 5 minutes. You can understand how much computing power this is that you need. It's hundreds of thousands of cores, of course, distributed in different areas of the world, which are running this simulation. That is a lot of money. And so what we also try to do is think of going towards setups where we say, well, can we speed that up? Can we actually be smarter? Do we really need to spend this much time to simulate what we want to see? It's a difficult question, because you need always to be very careful to not only simulate what you want to see, of course. So if you go to slide 16, and this is one project we're running since a few years, is thinking, how can we speed up simulation? Well, one of the things is approximate your geometry. Of course, you make a mistake. As soon as you start approximating things, you have to pay a price for it. The question is the price good enough? So you need to basically be able to propagate the simplification you make there into what it actually means for your measurement at the end. That's a very non-trivial part. Another reason to do that, in particular in a detector simulation, is optimize the transport and the navigation through this. Yeah, this is the second bullet on this slide. The next way better approach is approximate models. Cut off, if possible, cut off. But always you need to be able to think that what of an error am I introducing in the system by taking pi as 3, rather 3 point, that was pi day this last week or something. Fourth possibility is parameterize. Try to figure out what is a system, you have your distribution, you have measured your distribution, and say like, well, let's try to parameterize it. Let's cut it down to a few less parameters and simulate only those. Another one, that's number 5, take shortcuts. Wherever you can do, take a shortcut. And number 6, use new technology. Though when you use new technologies, always be aware not to reinvent those that are already there, of course. There's some more on the next slide. So if we go to slide 17. First point, how to speed up your simulation is don't do anything. If you don't need to do it, don't do it. That's the fastest way to work, is not to work. The second point is then, if you need to work only on demand. For simulation, this means don't try to solve the entire phase space, which is absolutely complicated, in one go. Make it on demand. A particle A with particle B probably is not correlated. Work on demand. The particle A is interesting. Work on that one. The third one is, if you know the answer, use lookup tables. You guys, I don't know, I actually have seen this when the euro was introduced in Germany. There was a grocery chain in Germany that had a table that made a euro to a Deutsche Mark lookup table from 1 to 20. It was 1, 2, 2, 4, 3, 6. Seriously, lookup table. Probably not the smartest one. In this case, I think a multiplication by 2 might be a faster way. Next thing to speed up your simulation is throw away things on the way. It's everything you don't need, throw it away. Forget about it. If you don't need it, throw it away. It's probably not a sustainable model for our society. I'm talking about simply simulation. Don't misquote me on that one. And the last one, which is for us very important, is ignore the truth. Ignoring the truth means the only reason why you do a simulation is because you want to basically go back and see what happens. Now, this is one of the most challenging parts in a simulation, is to relate the very beginning to the very end in a extremely complicated chain. We call that, from Monte Carlo simulation, Monte Carlo truth. This becomes a very complex tree to navigate through, and therefore slow simulation down. But if you just want to have the relation between the beginning and the end, which here I have the Homo australopithecus or whatever and the Homo sapiens, then forget the middle. So also don't quote me on that in other manners. This is basically my little introduction, and then I have like 3 more slides which show you that on a very simple example, which is on slide 18. One of the main problems to do is a particle goes through material and it will scatter. It will just scatter because there's material. You can imagine, even if you want to go through a crowded room, you being the particle, going through a crowded room, you will scatter. You will not go straight because there will be other particles that will take you out of your path. As simple as it is, whether it's macro or micro physics, it's the same thing. Well, there's a pretty formula for it. You can solve for it. What you can do though is if you go to slide 19, hopefully this works, you can run a little toy. Do you see the toy on slide 19? Okay, let it run once and I'll explain it. Okay, what I did here, this is usually what my students have to solve in their course. I tell them and ask them, prove me that the core of multiple scattering is a Gaussian distribution, and you need 5 lines of code. The smartest solution I've seen for that, I think, is a 3 or 4 line code snippet by a student. I'm way too old programmer already that I can do that in this, but I probably took me 10 lines, whatever. Who cares? Let me explain that to you. At the bottom, you see 10 lines. Yeah, this is our material. It's our detector. Our detector has 10 lines. We simplify the world. Always good. Simplify the world in simulation makes a big step. Our entire detector has 10 lines, and at every of these lines, a particle can scatter. So if you do that, you write a little small loop, 5 lines of code, write 5 lines, make 10 lines, and say every line you're allowed to scatter. And you don't even need a physics law for that. You just say you can scatter by, I don't know, minus 002 to plus 002, any random number, I don't care. If you run this 10,000 times, and that's the movie you've seen, you will see that the deflection at the end, most of your particles, the majority of your particles, will still have the initial direction. This is the probability is highest there. And then you have a nicely Gaussian distribution, which you can see with a Gaussian fit in it, with the probabilities to be very far off, lower, and highest in the center. Well, that's not such an amazingly new finding you have there, because I think that's also what you would expect. You shoot into one direction and then you randomly scatter, but if you scatter often enough, you might basically come out at the end of the room. Let's go back to our picture, having reached the door on the other side, even though your trajectory through this crowded room was scattered by other human particles. Very simple toy. If you want to do that, you can nicely take this parameterization, put it in, and instead of going 10 steps through this material, just drawing one random number, which speeds up your simulation by a factor of 10, not very surprising, 10 times, one time, and smear with a Gaussian resolution, and you are there having the exact same outcome in a stochastic manner. That is one of the examples. And then, yeah, I think that's it. On slide 20, I made it a bit more complex than for other people. That was like, if you start making the process a bit more complicated, with life is always more complicated, then it's not only Gaussian, you need to add some non-Gaussian tail, but that's a bit more interesting for physics students. Well, this is basically, I think we're at the end of what I wanted to talk to you. Yes? Yes, well, yes, particularly as you said, Sasha, that on the next presentation there will also be something shown, and I think by pure listening to it, it might not be such a thrilling event for me. Sure, sure. If there was a question,
No.
can you
Yeah.
just repeat it,
Okay,
Sasha?
there's no questions yet. But you don't. Your sound is okay, yeah? Because I'm a bit afraid of feedback. Okay. Are
Oh,
there
my
any
sound.
questions? There's a question. No.
Maybe I have a question.
probability. I mean, like what I'm really interested in is that a lot of the kind of like proof you do is very indirect, right? Or like odd, because like the popular imagination is that there's like a graphical depiction of the trajectories of the particles, but I mean, effectively it's all through data, you know, and then in a way what you do is to kind of like model the detector to, I mean, as far as I understand, that you model the detector such that you can actually prove, you know, like that the things that are signals in the data actually happen, which is quite far away from like the popular imagination of something like the LHC.
Well, if you found one of those events, that's what I tried to show you on this little particle physics course on slide 13. Yeah, if you found one of those events where these two particles just add up to 497.5 in their mass, then you haven't found anything. The only way you can actually prove you find something is by having it from a statistical point of view so convincing that it cannot be a random combination, and random combinations are there. Probability, sorry, is a bitch. You can quote me on that one. There can always be conspiracy. It just can add up that something looks like something, and it isn't what you actually think it is. This is the only way to convince yourself that you haven't fallen into a trap of a very awkward and evil probability density function is that you do it so often that you say, now it can't really be just bad luck or good luck. For this, of course, you can't define what bad and good luck is. There you have a mathematical framework, and you just say with a probability of, and we call that a sigma measurement, but with a probability measurement of 99.99999%, we have found it. That's what we have, very strict definitions. So we call observation of something new if we found it with 3 sigmas. So if you have a probability of 99.9975, then we call it observation. If we have something which is 5 sigma, which adds a lot of more nines there at the end, then we call it discovery. And this is like common knowledge in our field, and we need to be very careful with that. So something which is 95%, you will never see a particle physicist who would publish a 95% chance as having found something. It will not even be accepted in a journal. They will say, like, go back to your homework, find the other 5 dot whatever percent, then come back, and then we may publish a paper if it's well written.
Okay. There's one question from Dr. Gottlieb, who's one of the other panelists, actually.
Hello, thanks for the presentation. I just have a high energy physics history question with regard to simulation. So when I remember reading that in the early 90s, the LHC was being planned, and I don't remember, maybe you can tell me a little bit about the teams of physicists and how simulation worked into the planning of the experiment itself and the detector.
It is actually quite an interesting question, because that is repeating right now, because that's how our field works. Since it takes so long time to start up from the layout of the experiment to actually construction and having it, the timescales are 20 to 30 years planning, simple planning, before even technical design reports or project proposals or whatever can be written. So simulation is extremely useful and extremely needed for this sort of things. And of course, in all levels, yeah. I have not talked at all about the accelerator itself, because that's not my field of expertise, and I just don't understand how the people actually manage to get this machine built and deliver such a precise beam for us. It's amazing. But for the detector construction, we have a multi-stage system. So at the end, what we're physicists, at the end, we are paid by, luckily still, all the member states and basically the scientific community to do fundamental research. So our main interest needs to be, can we actually find something? Can we, with a machine of that type and a detector of a certain type, can we actually be able to either, in this case was mainly focused on the Higgs boson, or can we rule out supersymmetry and then make all the string theorists cry or happy? So the first thing you do is you make a feasibility study. You say, okay, we're gonna try it out and say, what happened if we ran a machine for 30 years and we assume very crude, this is the fastest simulation. You go back and say, let's assume we can build a detector that measures something like this to whatever, 10% energy resolution. Whether at the end it's then 8% or 6% or even 2% doesn't really matter, because you do a feasibility study. You want to know, is it worth it to go this path? So choose the fastest simulation and go through all the points I showed you, and then choose the optimal simulation. And once you're at that point that you're convinced, beside the fact that you need to go to the funding agencies and says, now we have a case, it looks like we can do it, all we need is a bigger detector and a bigger machine and whatsoever, and then you need to convince them, of course, to fund it. You start doing the second step and say, okay, now we need to prove that our feasibility study is also technological possible. And then you start doing the next steps and say, okay, let's implement a detector that doesn't even exist. But from our experiences, we know we can trust our simulation well enough to build a virtual detector, run the thing through, and invest a lot of time also to ask the different questions. How often does probability fool us, or how is our background, etc.? So you can see in all these steps, simulation is highly involved.
Any more questions? I think we should let you go. How's the reboot going? Last question.
Well, splash events are scheduled still for Wednesday, which means Wednesday should be the first time since 2 years that the beam is re-injected into the LHC. We'll see. This is not. It's not up to the experiments. We are of course ready and waiting, and from that on, that does not say that we are starting data taking on collisions in the next week. It's gonna take another few weeks to again learn the machine. The accelerator is entirely a new machine, and people who operate them need to learn how to operate it.
Okay, cool. Andreas, thank you so much for this technically challenging presentation. It worked really well.
Okay, good. Then I wish you a good
Thank you.
remaining day and have fun in Berlin. Bye bye.
Vielen Dank.